Hey, welcome everybody. Today we're doing a new experiment. Let me just first, let's just first introduce ourselves. So I'm Henry.
Hi, I'm Lori.
I'm Chad.
And I'm also Chad. I will go by the name of non-topology Chad for this.
Okay, non-topology Chad. Non-topology Chad, you sort of started this all off. So do you want to explain how this began?
Okay, well, like everything in my research life, it began on social media because I was on Twitter and I saw Chad post something about this exciting new paper. And so I clicked on it. It's called Persistent Extensions and Analogous Bars, Data-Induced Relations Between Persistence Barcodes. And so like this caught my attention. I think the reason I'm interested is like slightly related to my background. So like I've never taken topology. I use some topological data analysis in my work, mostly thanks to all of the other people in this recording right now. And so like I am a very applied mathematician and data scientist. And so I'm always just trying to keep up to date on the TDA literature and like understand what new capabilities are coming about. And so this to me felt like a really important paper, but I'm not necessarily equipped with all of the technical know-how that I need to understand it. And so I'm hoping that in chatting with Chad and the rest of you, I can basically like learn what sort of new capabilities or methods of analysis this work like might open up to me in very applied contexts.
Wonderful. So, I mean, the idea is, I don't think non-topology Chad, nor myself, nor Lori really know this paper well, but we wanted to ask Chad about it and get some explanations. And we thought it'd be fun to try to record it and hopefully to advertise the paper and help others, you know, yourself learn about the paper as well.
Yes, excited to learn more.
So I feel like I should say me too. You know, we've been developing the paper and sort of, you know, it's been 2.5 years of work to get this thing to the place where we were able to put it out in the world. And of course, you know, you talk to your co-authors, but it's not like you share it around to everybody in the community because nobody wants to put up with you developing all of these ideas. And so, you know, it'll be nice to see how other people understand this material and you know, get your feedback. So I'm very interested to talk about it.
On topology Chad, do you have any first questions or Chad?
Yeah. Well, I don't know. I mean, Chad, maybe could we just ask if you're willing to just kind of talk through the abstract with us and like maybe for me in a somewhat non-technical way if possible. But if that's too tall of an order, then please ignore that request. But maybe we could just like talk through the main idea.
Yeah, so I think elevator pitch version of the paper is probably a useful place to start. So, and maybe I'll just tell this is like a little story. So about, I don't know, a million years ago, when I got involved in all this applied topology stuff, you know, one of the first papers that I ended up doing in applied topology was this neuroscience paper, and the guts of that paper were essentially that there's this sort of organizational principle to neural activity, which has a very geometric flavor to it in a lot of brain areas. And what we wanted to do, so the way neuroscientists sort of extract that information is via a lot of correlation analysis. They get in there, get their hands dirty and like measure, I have a behavior and I have neural activity, and I'm gonna like very, very, very carefully work out what neurons are correlated to what piece of the activity. And it's a very linear process, meaning that, you know, if the coordinate system, if the structure of the data is highly nonlinear, this is extremely difficult and prone to errors. And, you know, it's taken huge amounts of work by very, very intelligent people to get that information. So, of course, the brain is highly nonlinear. So you want tools that are natively adapted to that context. Topological tools tend to be. And so what we ended up doing was building this whole machine that could detect these sort of geometric organizations in neural activity, you know, recorded from the brain of animals, which was super exciting and let us, you know, answer some cool neuroscience questions. Basically, but at the end of the day, it was a there, not there question. Is this structure there? Is the structure missing? And of course, it shows neuroscientists this, that's really exciting. So what can you tell us about, the way the brain codes complex information using this tool? I said, well, I can tell you it does, but I can't really tell you anything more than that, right? It's a yes or no kind of tool. What I would need to do in order to tell you more is use sort of the structure of persistent homology, which is the tool we used and the tool's paper is about, to sort of map things, so these behavioral correlates into the brain, or map brain region 1 to brain region 2 or something like that. Take the information encoded in these barcodes, the persistence barcodes, and sort of say, okay, this one over here is the same as that one over there. I know what this one means, therefore I know what this one means. Like that's the pie in the sky dream. So that's been, I think if I were to actually look at a calendar, I think it's 8 years we've been trying to do this. Because it turned out to be a little bit harder than I'd initially hoped. And
so can I break in with a question?
Of course, absolutely.
So is it basically like you want to know what feature in one barcode goes with what feature in another barcode? Is that the basic?
That's exactly right. Yeah.
Okay, got it.
Yeah. So you've got so we've got the barcodes, and I've got a bar, I've got another bar, and I want to say this bar and this bar are the same. Whatever the same means, right? Because of course, that even half of this paper, in fact, I would say the entirety of the paper in spirit is just answering the question, what are the words the same mean, right?
And
Related in some sense, perhaps. Yeah.
Is a good context like you have 2 point clouds, or maybe you have a point cloud that's moving in time and you have nearby times, and so you want to say that the barcodes are.
Yeah, and I mean the absolute simplest example is just you take 2 distributions. So let me take the uniform distribution on the torus and sample it twice.
I see.
Right, and there's no, and the problem is, right, in all, so my instinct as a topologist, as someone who grew up as a pure topologist, was to look for functoriality, which is like our secret secret weapon in all things topological. You say, okay, I'll build a map between these 2 topological spaces, and once I've got it, then I'll just push it down to the level of the algebra, because that's what the sort of homology always does, and then I'll just read off the answer. Everything will be great. But the problem is that if I give you 2 samples from a torus, or 2 a time varying system where I don't really keep track of the elements really well, or or 2 brain regions that have nothing to do with each other, there's just not going to be a map. Like the idea of having a continuous function between topological spaces is too ambitious. And so what you need to do is use some sort of actual data that you could get your hands on about those systems.
So can I tell you, I love this already. So like in my context of like biological experiments and stuff, like oftentimes we have like movies, right, of an experiment or a field observation or something. And it's like pretty easy to like get the positions of things in each frame of your movie, but it's like really hard to do motion tracking, right? To get like the trajectory of one thing. Like motion tracking, especially if you're working with fast moving things that are small and there's lots of them, it's like really hard. And so I think what I'm hearing from you is this is like a way to approach like topological analysis of, say, my moving biological system, like without having to have the data as the entire trajectory of each individual. Is that fair?
That's absolutely right. It will absolutely
Okay,
work
cool.
in that setting. Yeah. So the only data you need, right? So here's what I need. I need 2 frames or 2 systems or 2 whatever, right? You choose your 2 favorite things you're going to compute. And the paper we focus on the Viator-Rips complex, the standard like analysis, but honestly, we don't care what you compute as long as I have. So what I need is 2 simplicial complexes, 2 filtered simplicial complexes, and then I need a cross dissimilarity measure between their vertices.
Cross dissimilarity measure, what's that?
So okay, so I need, right, I've got system A and system B. So if they're Viator-Rips, my point clouds are my vertices, right? And I just need to know for every vertex over here, how similar or dissimilar is it to a vertex over here? So if I'm sampling things, frames in a movie or points in a metric space, I can just compute distance, and that's fine.
Can it be different numbers of points?
Yeah, there's no need for any But the two systems don't have to have anything to do with each other a priori, outside of the fact that I have the ability to take every element in one and tell you how similar or dissimilar it is to an element in the other one.
And you could define this in any way you want, but if the points are in Euclidean space, maybe you could just use Euclidean distance or something like that.
Right, exactly.
Okay.
Yeah. If it's 2
Nice.
points, if it's 2 point clouds in the same Euclidean space, you just take the huge giant distance matrix for all of them. I am so sorry. I have an incoming phone call for some reason that is not sorry. It's Wednesday,
Yeah.
right?
It's Wednesday.
Okay. Sorry, that was a scheduled phone call for Thursday. No idea what that was doing there. I might get another one in a moment from someone who is concerned about me not answering. I apologize. Anyway, yeah, so put 2 point clouds in the same Euclidean space, take the big distance matrix and break off the two blocks, and then break off the sort of, you know, AB block. And those will be your 3 pieces of data you need.
Mhm.
Okay, thank you. That helps me get it. Okay, so now I have, like, say, my 2 point clouds, and I have my similarity dissimilarity matrix. Okay, and so then what happens? I'm on pins and needles. What happens next?
Okay, right. Okay, so now I'm going to go ahead and compute the two, two barcodes, and maybe this would be a good point to show you a picture, because I feel like at this point we have enough pieces floating around. Let me just see if I've got a picture that is not too spoilery. We took, yeah, we the original version of this paper had, I think, 25 figures in it, and we pared it down to 8 or something.
Oh no, you gotta put the full version on archive or something. That's worth gold.
Yeah, I'm not sure. I think I might put the other figures on my webpage or something, because they didn't really end up fitting in the narrative that we had. You know, we kept cutting things out of the narrative to get the paper down under like 100 pages. And so, you know, we have all these crazy experiments. And I should say what I really mean is that Yoon, who is, you know, a gem of a human being and an absolute star researcher, like, put up with every single request I made to her. I was like, could you make a figure that does this? It's, oh yes, of course. And then off she would go, and she would come back and she had this beautiful figure, and then, you know, and then I cut them all out of the paper. So I feel like a bad person sometimes when I think about how much work other people do for me that I don't use. But I mean, at the end of the day, it really, you know, made the paper understandable to us, to see all these pictures. Well, okay.
And then the third author on this paper besides you and Iris Yoon is Robert Ghrist as well.
Yes, that's right. Yeah, sorry, I should have said that as well. Rob, you know, of course, is fantastic and does a tremendous number of things. So let me just share. Okay, I'm just going to share a figure from the paper rather than trying to dig out one of these old figures. I should have organized a bit ahead of time, but, you know, we didn't plan this as a planned thing. Okay, so this is just, oh, sorry. This is one of the figures, and I just want to, you know, pay attention to the right panel. So this is the idea, right? I have sort of the top and bottom there are 2 samples on a torus, right? And so the blue points and the gray points are just sample points on a torus, and then I've got this sort of north-south homology generator. And, you know, I look at a human being, right? This is the standard selling topology to people thing. I look at that and I say, oh, of course, a torus, and there's a circle that goes around it, and that's the circle. And those are the same circle. They must be, right? They're just deformed to go through the points in some way. And so what I'd love to do is just have a piece of mathematical machinery that tells me that and that are the same thing, right? And over on the left in the barcode, I feel like my screen, at least on my screen, is not rendering the top bar as being black. Is it rendering for you guys, or is it no? Okay, let me see if I zoom
Oh,
in
you
on
mean
that.
black instead of gray?
Yeah. Let's see if I can zoom in a little bit. There it goes. Okay.
Yeah.
Better. Okay. So anyway, and the point is, right, so if I were to, so how might I go from left to right? Right. I would take that top barcode that was spit out by my favorite persistent homology program, and I would say, okay, you know, let me get a generator for that homology class. And that's a whole extra story So Lori and Greg Henselman have been thinking very hard about that for a while, about various ways you can do that. But now, and me, but I'm I feel like I was a bit player in a lot of that. But basically all I want to say for purposes of this paper is it can be done, right? And nowadays I think Ripster will also do it, so it's not specialized hardware. But just to plug Greg's work, we built this entire thing on Irene, and the reason we did that is because we were able to get inside the guts and get our hands on a bunch of matrices that are normally destroyed by persistent homology computation. And to plug some other work with Greg and Lori and Haiben Hang, who was a postdoc with us, we are hoping to put out software that gives you access to those matrices in a native way, totally exposes everything in the near future. Been saying near future for about a year. So anyway, but you can get in, you get your hands on the sort of the algebra level. And say, oh, I've got this black bar, please give me representatives. And now I'm going to tell you that that's a lie. What I just said is a complete lie, because the barcode is actually not the faithful representation of the persistence module that you would really love it to be. It's up to isomorphism, right? If I choose a bar, then to get back to the persistence module, to get back to an algebraic element that I could unpack, I have to choose a basis of the persistence module, right? So this just tells me there are generators in different various, the bars say it's the birth and death of a generator, but there might be many choices of basis for the persistence module, which give you that particular barcode, right? Which express that isomorphism class. And so a lot of what this paper does, we know that people like to think in terms of barcodes or persistence. Some people like persistence diagrams. If you happen to be on the East Coast, I think you prefer persistence diagrams natively. That's sort of the historical rule. And so first you have to take, I like this bar, so you translate it down into the persistence module in all possible ways, and we provide an enumeration of those possible ways, which you can do in an explicit way if you're over a finite field. And then for each one of those, then you have to, of course, look inside the homology class and unpack. And so eventually you can take that bar and you can come back over here and say, okay, now in the point cloud, it's this north-south looking thing. And the same story on the bottom for the orange. So those are that's the goal. That's in our world, we want those two things to be
in the middle layer. You're looking at the union of P and Q. What's the difference between the middle layer on the left versus the middle layer on the right?
Right. So on the left, the cycle is still supported on the points P, and on the right, it's supported on the points Q. And so this is how we're right. So the point is that we need some sort of translation layer, some way to take points support, a cycle supported on the points in Q, and turn it into a cycle supported on the points in P. And what we end up using are something which we call witness complexes, which are almost the same as the thing that Ben De Silva and Gunnar Carlson called witness complexes, way back in the dawn of TDA, up to a rescaling. And it is my humble opinion that our definition of witness complex is maybe a little more accurate to the word witness, but because our goal is really about how do things in one see things in another. And it turns out that the data for a witness complex, and I'll talk a little bit more about what a witness complex is in a second. I'll just say the data for a witness complex is the data of a cross similarity measure. So in effect, the extra information that you want to build this translation layer is the information that we could hope to have, which is a wonderful coincidence.
And maybe I'm getting into the details, but roughly speaking, when you go from the picture on the top to the picture in the middle on the left. Why does the curve move? Like, why doesn't it just stay where it is?
Yeah, because it's not the same simplicial complex anymore, right? So the idea is we start on the Rips complex. So if you look on the far left there's this sort of sequence of things. At the top, we've got the barcode of XQ, which is our notation for the Viator's Rips complex supported on Q. And now we're going to move to, and we're not actually going to, we've shown the barcode for the witness complex there, but we're not actually going to use it. We're going to sort of go around it. Because translating back to the barcode requires doing this change of basis thing, and we don't need to do that. So we're just going to shunt around it. But when we move from the top column to the middle column, we're leaving one simplicial complex and moving to the witness complex, which is so roughly, right? The witness complex at scale T is consists of so it's witness QP. So that's witnesses on vertices Q, simplices on vertices Q, witnessed by vertices P. And so at scale T, the way we define that is just all subsets of vertices of Q, which are within distance T of some vertex in some single vertex in P, right? So every bit, you just imagine, growing balls around points in P, and in each ball you look at all the things in Q. That's a simplex, right? And so at the end of the day, right, for any given scale, the simplicial complex that you see there shouldn't be the same as the clique complex, right? There shouldn't be. There's no reason to expect those two cycles to look the same because the underlying simplices are probably not the same.
Okay, can I break in and try to re-articulate my understanding, which is quite possibly not correct? And especially because I don't really know much or honestly anything about witness complexes, but here's what I think I hear so far. So you start with the data on top in Q, and like you look at the barcode and you're like, oh, there's like an interesting feature, and like there's this business about like how you get a generator, which you said is sort of a lie, but whatever, like somehow like there's this thing we're interested in, this north-south feature that like goes from top to bottom. And then you have your other point cloud at the bottom. And so what you're doing is sort of like trying to, in a way, bring them together. And the way you do it is through witness complex, which means that you kind of like superpose both things as you're doing in that picture on the left of the middle layer. And there's some scale that goes around, you put balls around the points of P, and you take the like points of Q that are within those balls. And then I think this is where I'm stuck. Can you?
Yeah, so imagine for just a second that P consists of a single point.
Yeah.
Then here's how I'm going to build my complex. I'm just going to take that one point, I'm going to grow a ball. And at each scale, I'm going to take all the points at Q and call that my simplex, right? And that's the only thing in my complex. It's just this one simplex that gets bigger and bigger and bigger and bigger as I see more and more points of Q. Right, so that's a complex, that's a simplicial complex supported on the points of Q, but sort of indicated by this point of P.
Right.
And so for every point of P, I'm going to do the same thing, and I'll just take the complex that is sort of the downward closure of that. Right, I'm going to add in all the lower, or all the ways that they intersect. I'll put all that stuff in.
Okay, I think I get that enough. I don't know what downward closure is.
Oh, sorry.
No, it's okay. But I think I get it enough to get the idea. So that was very helpful. Okay. Thank you.
Yeah, absolutely. Yeah, so, okay, great. So any other questions about that little bit right there? No.
And then you don't need to get into the details, but do you have a map from the RIPS complex to one of these witness complexes? Okay.
Yeah, so that's where the guts of, so there are two major steps here. So the map is not a map in the, right, so this is the problem, right, is that I as a topologist, I always want to go back and be like, I'm going to grab the map and everything's going to be great. But here there's not an explicit map. So we have to be, the reason we get relations and not, morphisms is because at the end of the day, every piece of this puzzle relies on something which is not a map of simplicial complexes in any effective way. Yeah, so So yeah, so let me just tell you a little bit about the extension method, which is the way we get from the top to the middle. And let me just see if I can find a figure that is useful for that. It's the extension method figure. It's the output. Right, okay. So here's a simpler picture where what I've got is, right, so now I've just, instead of sampling the entire torus, I've just sampled this left-right thing, right? And I've got a cycle sort of supported on that. I want to just know how it maps into the barcode on the torus. And I am glancing at this and realizing that this figure is meant to demonstrate a whole lot of things that are technical about the change of basis, but let's just ignore most of the detail here for a second. I'll just tell you what happens. So right, so okay, so I have this, you know, this Q which I've sampled along this left-right circle, and what I want to do is okay, sorry, I was just getting my P's and Q's in the right order. You know, so whatever you're supposed to, crossing your P's and Q's or something like that. So, okay, so you'll notice that the barcode there is not either the barcode of the witness complex or the clique complex, right? It's some crazy intersection of things.
Oh,
so,
on that label in the middle.
Yeah, exactly, on the label in the middle there.
Yeah.
And so, right, so of course what you want is a map, but you will never have a map because a priori these are just different complexes, but they're supported on the same vertex set, and that's kind of our way in. So what we end up doing is saying, okay, suppose you give me you know, this cycle that you're interested in, that lives on the elements of P. What I can do is I can open it up and I can look at a representative, right? And it's going to be some collection of one simplices supported on P. And what I really want to do is you know, is that the same as some cycle? And again, cycles are equivalence classes, right? So I've got many of these that are all sort of represented in this other complex, right? So I have these two complexes. And in this case, they happen to be supported on the same set of vertices. And so what I'm going to do, so say, well, you know, there might be, you know, so you can imagine sort of in like a worst case scenario that your points in P are sort of banded across, right? So there are lots of circles in P that sort of show up and they look like, you know, that sort of for a while appear to be different, and then they'll fill in. Right, so imagine just a bunch of like thick bands of left to right points in P instead of having them sort of nicely smeared. The persistent homology that would look like, you know, there'd be a whole bunch of cycles that would then glue together and become one big cycle.
So you go from a stack of circles to like a cylinder. Sort of.
Exactly, yeah.
Okay.
And so right then, if I ask you which one of those is the left-right circle, I don't know, right? So it's not really, you know, and then that's the kind of thing we want to be able to say is all of these might potentially be the left-right circle that we're interested in. So what we want to do, right, we want to say all, you know, consistent with what I know about the cross, you know, or maybe what I want to say is it's most likely to be the middle one because that's where my points are sampled, but all of these are potentially left-right circles. So they all have some chance of being the one we're interested in. Right, because maybe today maybe the reason it's banded is because at different times the measure is concentrated at different points along the cylinder, and you know, when I came along and measured it, it was here, but later if I'd come back, you know, in the evening when the tide was low, you'd have measured it down here. And so, you know, I don't want to discard that possibility. I want to use the information intrinsic in the complexes to say these are all possible matches. So what I want to do is sort of pop open these homology classes and say, okay, these homology classes contain representatives that are eventually homologous, that they're eventually equivalent to the one that I observed in my original thing. So we're just gonna ask that question. We're gonna say, okay, given your witness cycle, let me make that as big as possible without being trivial, right? Let me go out as far in the filtration as I can. Until such time as, right, so the death, I'm gonna come in right before that cycle dies. I'm gonna push to the end of its bar. I'm gonna say, okay, now this cycle is as big as possible. So I'm being as permissive as possible about things in the witness complex that are being witnessed by the points that I saw. So right, I haven't filled up the cylinder and therefore emptied out, or I haven't, in the cylinder examples, maybe not so great because it's hard to trivialize. But imagine, that I'm filling in also inside the cylinders and things will eventually collapse.
Mhm.
So I'm gonna make my class as big as possible. I'm gonna take that entire pile of representatives, all of them, which is huge, right? There's a lot of possible ways to bounce along those one side. So I'm gonna take the whole thing. And what's gonna save us is that I don't have to think about all of those. I can do some fancy linear algebra and think about affine subspaces and just solve some stuff about basis elements. But the idea is to take that entire list and then go to the other complex, right? Go to the clique complex, which is the thing I'm actually interested in, and say, okay, for each of these, which class is it in? So that's me going back to the geometry and saying, okay, I've got these highfalutin algebraic equivalence classes. They're all very complicated. But what I could do is just take every element of this class and figure out which pigeonhole them into classes in the other complex.
And how do you pigeonhole them? Just by looking at similarity somehow?
Right. So in this case, what I'm working on is so I'm using the witness complex, right, which is already supported on the same vertex set. So I'm literally just going to ask for intersections, set intersections of homology classes. So this homology class contains this representative, and so does this one. Even if even if all but one of the homology or of the representatives of the class are disjoint, I just want to know that there is one representative in common. Right. And since this is built out of since the one complex is built out of my cross similarity matrix, right, out of my similarity measure, that's telling me that according to my similarity measure, it is possible that the thing that I saw was in this class. So I know it's a lot to just say out loud and wave my hands about, but again, just I want to point back at this picture, right? So I've got that, right? I've got the Q, and that's the thing that I came in and measured, and I was like, okay, this is the thing I want to sort of compare elements. I've got these two homology classes on the torus, and I want to know which one I'm looking at. You go ahead and compute persistent homology of the point cloud P, and you've got these two bars, and you want to know which one I'm thinking about, right? But maybe when you computed persistent homology on P, right, the natural representative you would have seen, because the point cloud is thicker, is way up at the top or way down at the bottom. Maybe it goes diagonal, right? But if there's some representative in there that's sort of the one you want. But it's equivalent to many, many more over the course of the thing. And so eventually it'll be equivalent to one that's kind of the same. And the witness complex, on the other hand, right, is starting concentrated around there, and then it's growing these things out. And eventually there's a moment right before that cycle fills in, when it sort of fills up the torus, where it's going to contain all of the possible horizontal representatives and in all the diagonal ones and all sorts of other things. Right? It's huge. What we're going to do is we're going to take, at that moment, we're going to come in, we're swooping, we're going to pick up that class, we're going to pop it open, and we're going to take that entire list. And now we're going to go back to the Viator strips complex on P, on the points of the torus, and say, okay, give me a list of every possible persistent homology class that contains a representative in this list. Right. So you'll get your natural one, your first one, which is the crazy one, but you'll also get many, 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 many more persistent homology classes as various little cycles fill in, that all give you a sort of things that could have been the one that we started with.
And let me zoom out for a second. So what's the final output? Is it you have two barcodes and then you have sort of a partial matching between them? Is that the output?
Yes, that's right. So it's a set relation between, so it's not a matching in the sense that we don't, it's many to many.
I see. So I could be a bar that's matched to many other bars, or I could be a bar that's matched to no other bars.
Exactly.
I see.
Yeah, we're very and the basically, so it's there is a big relation built this way, and when you select a particular bar, then you're going to ask what is this bar related to in the other set. But you could also ask the other question using these tools. You could just say give me all of it, right? And that's a massive computation. I would not actually you would not want to ask that question.
I see. Usually you ask it one bar at a time.
Yeah,
and then sometimes maybe I got this impression from one of your figures, or maybe I'm making this up, but sometimes I'll have a bar that by design might be matched with a bar that doesn't even overlap in terms of their scales. Is that right?
Right. So the thing that's sort of our why is this something we're going to do question picture.
That's sort of like a motivation. You sort of want this sometimes, right?
Yeah. So right. So up at the top there, I've got 3 different samples of points on an annulus. Right, and then one at the far left is really tight, sampled from a distribution that's really tight around the center, and the second one's sort of bigger scale. But the second and third are actually samples of the annulus from the same scale. And we didn't have to do this a bunch of times. Like this is, I think, the second and third time we ran this thing, we got these 2 barcodes. So it wasn't like this is not an uncommon thing if you have a kind of sparse sample. And what happened, so you'll see sort of that of the 5 barcodes layered there, barcode of Q is sort of way up to the right, and the barcode of R, the one on the right, is sort of in the middle. And if you try to do any sort of naive homological algebra, then what ends up happening is you have to match things, and there's some very, very pretty work showing you like what happens if you assume there are maps. Then basically bars have to match in scale. You can't get away with bars not matching in scale, which is a problem because I think Q and R probably should, I should be able to match the bars in Q and R in any sensible world. So you try to do things like take unions or intersections. Well, you can't take intersections because there's nothing to intersect. But if I want to take unions of these simplicial complexes, what ends up happening is that sort of fourth bar, you'll always sort of collapse down to the smaller scale. Because things will be born when they're born at the latest will be born at the smaller scale, and so in effect you can't get a night the sort of the thing you would want to do, and the thing that I wanted to do for the first 6 months or so of this project before I gave up was find a way to use a union. So we needed an intersection at the end of the day. Like that's what you really need, is to think about intersections, but then you need a simplicial complex in which intersections make sense, which is where the witness complex comes into play. Right, because to do intersections, you need to be supported on the same vertex set. Otherwise, for simplicial complexes, you're just out of luck. So,
gotcha. That's pretty cool. I like that a lot. Yeah. I mean, I see what you're saying. You want those bars to be matched because they're both corresponding to the hole around the annulus, but it's hard to do because they don't overlap in scales.
So this picture is sort of illustrating why you can't use the unions and why we need to go to the witness complex and then do an intersection.
Yeah, exactly. This is our one of many pictures that we have that came from our attempts to our failed attempts to do simpler things. And as far as I can tell, I got to be honest. As far as I can tell, this is the simplest thing that could possibly work. Which is not what I would have wanted to say 2.5 years ago, but here we are.
Have you tried this on any data sets yet, or is that for the future? This is
yeah. So we have. So this back in the. I should say, by the way, we haven't actually solved the problem yet. But we've only just done this funny thing where I take a clique complex and move to a witness complex, which does not relate to clique complexes.
Right, but I mean, maybe don't get into the details of Dowker duality, but then I saw you use Dowker duality to go to the other vertex.
Exactly. So we can do it twice, right? And what Dowker's theorem tells us, which is really nice, let me just quickly say, is that if I take the cross similarity measure, and I think about points supported on P, witnessed by points of Q, and the ones with points on Q supported on, witnessed by points of Q supported on points of P, those have the same barcode. And then it turns out there's an explicit isomorphism that lets you map homology classes back and forth. So we implemented that explicit isomorphism, and that now you have an entire chain, right? I can start at the top, match to things. So what I do is I start at the top. Well, there are two ways to do this, and we sort of discuss both. You start in the middle on the witness complex, and then I choose a bar, and a long bar in the witness complex is saying something like there's a very strong matching between topological features, right? There is some strong relationship. So what is the strong relationship? Well, let me match out in both directions, right? And that so that gives me a relation between, so then I said, so you imagine I'm matched through this bar. That wasn't actually what I wanted to do when I got started. What I wanted to do when I got started was start at the top and get down to the bottom. So what I could do is I could take this bar, match down here. Now I've got many possible bars, push them all through Doppler duality, get a bunch of bars, and then match all down here. So the problem with that is, of course, it ends up being a bigger list, right? And possibly much more relation looking. But it is, so you can run this either way. We provide details on how both work, and so I just want to briefly say that we have a complete method basically from getting to the top to the bottom or from the middle out, and both of those are gonna work just fine. And we play funny games, so you can take this. So this is just the method of matching things. So for example, if I do dimensionality reduction, then I still have the same vertex set, so I don't have to do all of this funny bouncing through witness complexes. I can literally just apply the first method, the extension method, to compare what things intersect, and I can see that, for example, the cycle in that trefoil, when I flatten it onto the plane, kind of gets represented in all of those different bars.
Oh, cool.
But
so this is easier. There's fewer steps whenever you have the same vertex set.
Exactly. And then you just have to do the one thing, get just like a one directional relation. Everything is. So
that's sort of non-topologist Chad's context often with time varying.
Exactly.
Mm-hmm.
Yeah. And this is so cool because in my context, we're often so interested in knowing like what happens, say, to like a specific group of organisms. Like at some point in an experiment, like this cool thing happens and these organisms do something. And then like maybe at some other point it stops. And like knowing that that's what's happening in the data when there's a lot of data has been really hard, right? So we've just been looking at like Betty numbers and being like, oh, there's like, this many groups here. And like now there's like one fewer group or something. But like the ability to be able to like actually track those features through my data seems just like awesome.
Yeah, I mean, that's exactly what so I should say in this setting, right, what Chad said earlier, Nontopologist Chad said earlier, is that one thing that's hard is keeping track of who's who. And so I should say, right, you have to keep track of who's who to get away with playing this game this way. But if you lose track of who's who, the other method will still get you there. You just have a little more computing to do.
Right. And that's actually like, I'm willing to do more computing because that is a huge capability. I mean, like I foresee this being so concretely useful for me, selfishly. And so the software can't happen fast enough,
Well, there's code already to do this.
Love it.
You can so we, the code that Iris sort of built on top of Irene is available. You can get the link at the top of the paper. You can just take your code. I should say, you take your data, and if it's small enough, you can plug it into that code and it will do the thing. If it is too big, then we have thought really hard about how to optimize. And so there are a lot of things that end up matching through a lot of cycles, just because you get a whole bunch of sort of tiny noise cycles and those things. So what you can do is, if you're pretty sure that those noise cycles don't aggregate to create new interesting answers, you can tweak the code to make it basically ignore cycles under a certain length, bars under a certain length. So
oh, that's That's really useful. Okay, cool. And then I know probably the answer is like, it always depends on the configuration of the data, but can you give me any sense of like what the data being small enough for this code means versus not? Like, what is there, like some order of magnitude I should be thinking of?
I wouldn't try to run this on 1,000 vertices. I think, but I think all of our examples here are on 100.
Got it.
And like I think, yeah. So these are 100-point samples on the torus, I believe. Yeah, I would. So the way that you can find out is if it's going to work is it will probably almost immediately crash if you try, because like one of the first enumeration. Also, yeah, one of the things that's going to happen, right, is the way it explodes is in terms of linear systems you have to compute. And so if it's too big ever to run, then the first time we try to build these matrices, it'll just implode and you don't have to worry about it. But it may take, based on the number of linear systems you end up needing to solve, and that's where cutting off the short bars comes in. It may make it very long runtime. So this is something that would be easily parallelizable, but we didn't do that.
Oh, you just anticipated my next question. Okay, thank you.
Sure.
Related to this, a question I was thinking of is, like I look forward to learning the math here, but some of your users will not, fully dig into the math. So do you have any tips for those folks who want to use it? I guess one tip was, consider eliminating the small bars, which sounds like a really good idea.
Yeah, so we the way we wrote the paper is basically the algorithms are in the main text, and the definitions you need to understand the algorithms are in the main text, and all the technical proofs that you would want to know if you were thinking about the math are pushed to the appendices. So I think the paper, I won't say it's easily readable by a general audience, but what I will say is we did our absolute best to make it so that you don't have to have, a background in homotopy theory to get at the paper. You need to be conversant in the basic ideas of persistent homology and combinatorial topology that you would need in order to do basic computations. But I think if you've got that and resilience in terms of indexing, you can survive reading the paper and just let your eyes kind of glaze over when you actually read the algorithm the first time, because it's every time I read it I have to remember what it's doing. It's just it's technical. It has to be technical, right? But the guts of the story are set up and solve some linear systems. And so I would say, if you're not a person who is deeply comfortable with the machinery of algebraic topology, you could play with the code on examples and get a pretty good feel for what's going on. And I think sort of reading, in particular, the motivation sections are meant to be largely non-technical. The first section, let me just remember, I think section 4 is our other, section 4 is where we introduce background. Section 3, maybe. Yeah, this section here, understanding the problem, is meant to be, if you're comfortable with a little bit of notation, this will tell you what we're trying to do and why.
That's a good title for a section.
Totally. Well, speaking of titles, I was going to say, Chad, I know your paper has a title already, but when you give talks about it, can the subtitle be "Mind Your P's and Q's"?
I should. I try to avoid ever using the P's and Q's. Like, we put them in the paper because you have to name them things. But oh man, if I ever give a talk where I've got to unpack this thing, I have no idea how I'm going to possibly avoid constantly getting everything. I don't know. I do my best never to put letters on slides, but man, I should. Maybe I give a talk about talking about this.
So I personally will have to get going and not too long. I was thinking maybe we could wrap up just with last thoughts from folks. I don't know if somebody wants to go first.
I mean, Lori, do you want to go?
Yeah, I think I have a general sense of this, and it has the power to be really useful. I've worked with Chad on a few of these biological systems, and I can see a lot of applications there. So Thank you for explaining this, Chad. Topology, Chad.
Yeah, and Chad, I agree 100% with Lori. Like I said earlier, when I saw this come online, I was like really excited, but not, I was nervous about trying to understand it, and you made it really accessible to me. And I think like for the kind of work that I do, like this is going to be kind of amazing. And honestly, like I'm working with some people on honeybees right now. And as soon as this video that we have made goes live, the very first thing I'm going to do is send it to them and be like, y'all need to watch this. So yeah, thank you so much for this work and for explaining it to us.
Yeah, thanks for the personalized introduction. And I like the motivation of being able to match cycles or bars that don't overlap, but or I mean, in simple cases, they should be related, but maybe you're trying to tease out those relationships in more complicated situations where you don't know that before. That seems quite powerful and a really cool idea that I wouldn't even have thought was possible.
Yeah, well, thank you guys all very much for the opportunity to ramble at you. And of course, my general motivation when I'm doing math is to be useful to other people, particularly applied people, because that's kind of how I've found myself oriented in life. So both to you guys and anybody who watches the video, I am more than happy to help you get this thing up and running as much as I can, and discuss problems. And the last page of this paper is just a gigantic list of things we didn't do that need to be done in order to make this thing go. Questions about stability and what happens in various cases. And the other thing about this paper is it's like a definition in some sense, right? Like the entire paper is a definition that we didn't prove all the theorems that we need to prove. So I also want to invite everyone who is more of a pure math person. There's a lot to be done here, and there's no way I'll ever have time to even get started. And I'm happy to talk to anybody, but in particular to you guys. It was wonderful to have an invitation to do this, and great to see you all after all this time. So.
Thanks, everybody. See you all.
See you. Thanks.